Friends, we are in the 8th quarter of complex numbers. Here we are going to roll through the complex exponential function and the complex trigonometric function. In fact, we are going to roll through quite a large number of points wherein we are going to define exponential complex function. We'll study its properties, in detail, mapping of these complex functions, understanding the mapping. We'll try to understand mapping graphically. We'll study the inverse complex exponential function. Then we shall attempt complex trigonometric functions which depend upon the exponential function. We'll study properties of sine and cosine functions. We study the formula for addition, subtraction, proof of that formula, some properties related to that, zeros of the sine and cosine function. We shall differentiate the sine and cosine function, and we shall relate it to hyperbolic function. So complex functions we are going to write in terms of the real trigonometric functions and the hyperbolic functions. So complex exponential function, this is not new. In the last quarter we have written this function f of z is equal to e to the power x cos of y plus I times e to the power x sine of y. You can take liberty to take e to the power x common, and then you can rewrite that as cos of y plus I times sine of y. So here the basic variable z is a complex function, complex variable that can be written as z is equal to x plus iy. So this is an entire function, as we have seen. In fact, it is analytic function for entire domain of complex numbers. So we are calling that as entire function. Now that, let us try and study how this function behaves when y is equal to 0. When we substitute y is equal to 0, then cos of 0 will be 1, sine of 0 will be 0. So we are left with only a real part, that is e to the x. So f agrees with a regular exponential function in the domain of real numbers. However, as I said, you can factor this equation e to the x, we can take common, and then this quantity cos y plus e to the plus I times sine of y, we can write as e to the x into e to the I times y. So here we are in position to make definition of the function e to the z. So this obviously we can write e to the x plus iy. So this makes z. So we have written e to the z, sometimes also denoted by exponential of z, and it is defined as e to the z is equal to e to the x into e to the iy, where we can write z is equal to x plus iy, which looks like e to the z. Let us try and explore properties of this exponential function e to the z. Obviously, e to the z is equal to e to the x into e to the iy. Now we are interested in finding mod of e to the z. So when we are taking mod on both sides, mod of e to the z is equal to mod of e to the x into e to the iy. So modulus of product of two entities, two functions, is equal to modulus of their product. Now we shall try and understand this e to the power iy. E to the power iy is equal to cos of y cos of the angle y plus I times sine of the angle y. And when we consider mod of that, then mod of e to the iy we are interested in finding. So it will be under root of real part square plus imaginary part square. So cos square y plus sine square y. So you can obviously see that cos square theta plus sine square theta, that is always equal to 1, and under root of 1 is equal to 1. So when you try to chart this in the complex plane, then e to the y will lie somewhere on the circle of radius 1, and that makes an angle y with a real axis. This is the angle y, which is made with the real axis and denoting by x, and this is imaginary axis, which in general we are talking in terms of y, but this time our angle is y. So y is the angle made by the position vector of a point. So here that is the point we are defining, which is at the distance unit. It's on the radius of circle 1. That's it. Now this quantity is unity, so we don't have to bother for this. Then mod of e to the x. So let us try and plot the x variable on x-axis. I'm talking about now the real function, real exponential function, that is e to the x. So here I'm plotting e to the x on this dependent axis, and now you can see that it cuts y-axis at 1 when x is equal to 0. When x is equal to 0, e to the 0 will be 1, so it has value 1, and as x increases it rapidly goes up. So this has asymptotic behavior with your x-axis in the second quadrant. Therefore, this function is never going to be negative. So you can drop the mod sign and you can strictly write e to the x. So mod of e to the z is simply equal to e to the x. Now we are interested in looking at argument of e to the z. So argument of e to the z, as we have written, e to the z is equal to e to the x into e to the iy. So argument e to the z is equal to argument e to the x into e to the iy. So whenever we are writing the polar form of the complex number, so this is another complex number, w, which I am saying it is e to the z. So this we can write as a combination of some pre-exponential factor kind of r, which is distance of the point from origin, and e to the power I times theta. So here e to the x is forming some radial interval. So this is to be ignored for finding argument, and the argument is y. You can see that the argument is theta here, so here the argument is y. So argument of e to the z is equal to simply y. But to be more precise, I should write this is 2 pi times k, where k is an integer, so that it takes care of everything. Now in the next property, we have added 2 pi I to the number set. So when we are adding 2 pi I to this number, so it means that we are adding I times 2 pi. So here we are left with x plus I times y plus 2 pi. So this is what we have written in the next step, that it is e to the x into I times y plus 2 pi. So when we are adding 2 pi to the argument y, we reach to y again, because here our cosine and sine functions which are involved in the definition of e to the I theta equal to cos theta plus I times sin theta has a period of 2 pi. Therefore, we can take liberty to write that as e to the I y. So this returns back to the original function e to the z. So e to the z plus 2 pi I is equal to e to the z. Thus, here we conclude that the function e to the z is also a periodic function, and the period we normally write in terms of capital T, that is equal to 2 pi I. So the exponential of z function, which is a complex function by definition, has period of 2 pi I. Now, let us try and understand e to the z plus w. So obviously, by laws of indices, we can separate these two quantities. Before doing that, we shall write e to the z plus w is equal to e to the x plus iy plus u plus iv. So here z we have replaced by x plus iy and w by u plus iv. So obviously, we can tackle this in a way we can collect the real parts together and imaginary parts together to have a simplified version. And further we can simplify that to separate these quantities so that we can obviously write e to the z into e to the w. This is following the rules of the laws of indices. So further we are extending our ideas of this exponential function, and 1 upon e to the z is equal to e to the minus z. So let us suppose that we have two functions and we are taking product of them, e to the z into e to the minus z. So obviously we can write e to the z minus z. So e to the 0, anything raised to 0 is 1. Now you can divide this equation by e to the z on both sides. So here e to the z and here in the denominator e to the z. So here e to the z from numerator and denominator is cancelled and we are left with this product. Now e to the z is an entire function. This we have already shown in one of our earlier slides. Now we shall recall derivative. E to the x into cos of y we have considered as a real part, and e to the x sine of y we have considered as imaginary part, and we have written w is equal to u plus I times p. So here we are going to differentiate this and we are going to use the Cauchy-Riemann equation. Now first derivative we are going to find of u with respect to x, treating y as a constant. So in fact we are having partial differentiation of u with respect to x. Derivative of real function e to the x is e to the x, and cos of y is being treated as constant, so remains as it is. Then partial derivative of u with respect to y. So here e to the x remains constant, and derivative of cos of y is minus sine of y. That makes it minus e to the x into sine of y. Similarly, we are going to differentiate this v with respect to x. So again, e to the x will have derivative e to the x, and sine of y is a constant quantity appearing as it is. And derivative of v with respect to y, e to the x will be constant, and derivative of sine of y will be cos of y. So obviously, from our earlier section, which was 7th, in which we have discussed this, f dash of z we can write as partial derivative of u with respect to x plus I times partial derivative of v with respect to x. And here we have these quantities. You can see that Cauchy-Riemann condition is valid here. So these quantities are equal, and these are equal with a minus sign. So I'm using different notation that we have a minus sign while quoting this. Now f dash of z we can write as e to the x cos of y plus I times e to the x sine of y, and it is obviously e to the z. So this exponential function when differentiated has the same function, so it is behaving the way it behaves for real functions. So the derivative of e to the z is e to the z, and the symbol we are using for differentiation is d dz of e to the z is equal to e to the z. Now we are into even more properties of the complex function, which is in fact exponential function. Now d dz of e to the power az, where a is a constant quantity that belongs to the set of complex numbers. Now here this quantity e to the power az we can write as e to the a into e to the power z. So here we can employ the chain rule, and derivative of e to the power a will be simply a times e to the power a. So this a times e to the power a will be the derivative. So we can write that as a into e to the power az. Now we have e to the power complex conjugate of z. So complex conjugate of z we are interested in. Z is equal to x plus iy. So conjugate of that z will be x minus iy, and we can factor this as e to the x into e to the power minus iy. So here this angle y we are considering, we'll go back to the basic definition wherein we have argument y. So horizontal axis is a real axis, and this one is imaginary axis, and we are locating some point here that has argument y. So this is that. And then we are interested in locating minus y, the same angle below a real axis. So this forms a complex conjugate. So this is e to the I times y, and this is e to the minus I times y. So they are complex conjugate. So here e to the minus iy we can write as complex conjugate of e to the iy. E to the x is a real quantity, so we can very well take liberty to put a bar making a complex conjugate of the real number because it remains same. And product of two conjugates we can write conjugate of products, and we can write conjugate of e to the z. So in this property we are trying to locate the points where the exponential function e to the z takes unit value. So obviously e to the z equal to 1, it means that e to the x into e to the iy is equal to 1. So e to the x, this is a polar form of the complex number, and this is a radial part, and e to the iy, it means that argument is y. So e to the x inside bracket we have cos of y plus I times sine of y. So here we have to look for this form. Now this is equal to 1, it means that this quantity should be 1, and cos of 0 is 1 and sine of 0 is 0. So here we look for y equal to 0. Then when y is equal to 0 and x is equal to 0, then this is unity. So the complex number in polar form in that condition will be 1. So to be very precise, when this cos of y will be 1, cos of y will be 1 when y is equal to 0 or y is equal to 2 pi or y is equal to 4 pi and so on. Similarly, at those points, sine of y will be 0. So obviously, in a very generalized way, we should consider x is equal to 0 and y is equal to 2 pi k, where k is a number, integer. And then e to the z equal to 1 has a condition that this x is 0, so z is equal to x plus iy, x plus iy. So x is 0, so this is vanishing, this is 0, and this y is replaced by 2 pi k. So 2 pi k should be the value of y for the exponential function to reach to unity always. Now what are the conditions when e to the power z is equal to e to the power w? So this is possible when z is equal to w, or we already know that the period is 2 pi I of the exponential function. So z must be equal to w plus 2 pi I. So let us explore whether something more is hidden into this relationship. So what we do, we divide the equation by e to the e to the w. We divide the equation by e to the w. So this divided by e to the w and this divided by e to the w. So e to the w upon e to the w will be 1, and here we are left with e to the z minus w. So z minus w must be equal to 2 pi I k. We have seen it here, and therefore z must be equal to w plus 2 pi I k. Now we are in position to discuss the mapping of complex exponential function. It's a very interesting topic. So here we have a function w is equal to e to the z. So we are interested in mapping z plane, which is x plus iy, belongs to the set of complex numbers, to the new plane, which is again a complex plane, that we are going to call as a w plane, and here w is equal to e to the z. So what are the images of the horizontal lines we should first see? So how do we designate horizontal lines? Horizontal lines we are representing by L equal to x plus iy0. So here y0 is fixed, y0 is not changing. So only x can roll from minus infinity to plus infinity. So x is changing from minus infinity to plus infinity, and y0 remains constant. So we are considering locus of points which are parallel to x-axis, and here obviously x is the part of real numbers, and y0 is also part of real numbers, but they are fixed, they are constant. So e to the, we are interested in w, e to the z. So e to the z will be e to the x plus iy0, and here this is the polar form, which represents a radial part e to the x, and it is multiplied by e to the power I y0, where y0 is the argument, that is the angle made by the line with real axis, and that remains fixed. This is going to remain fixed. Now let us try and understand that. Here we are considering, first of all, we shall consider that we have a line which is represented by the argument pi. So here we are talking about this dotted line. So we are talking about this dotted line which is having y value that remains constant, that is pi, and then we have what we are calling that this y0 is being replaced by pi. So e to the power I times pi we are talking about, and obviously this has numerical value -1. So we are on the another axis. So this is the line which is corresponding to the highlighted line, and this makes an angle of pi with your x-axis. So this is making an angle of pi with x-axis. I want to mention that this is accepting the origin. So this origin should not be included in the discussion. Now next we shall consider this line. I'm talking about this green line. I'm trying to highlight that this line is just above the numerical value pi by 2. Here I anticipate that this is pi by 2. This is pi by 2. So here this green line, dotted line, is just above the line pi by 2. Now here the line that makes an angle little above pi by 2 is this one. So I would like to highlight that line, which is this line. So let us look at this line, which is at distance around pi by 4. So this pi by 4 line, you can locate that it is this line. Similarly, let us look at some another line, which is say yellow in color. So this is the line little above pi. So I just want to highlight that, and I'm spoiling it. So here, can I get this? Okay. So I'm talking about this line which is above pi. So this line obviously reflects here this one. And here you can see that it makes angle a little more than pi. So this is the angle more than pi we have. So when we try to locate the same line, which is here, which is little less than pi, so this can be represented by this angle little less than minus pi. So here you can see that these two lines, they are reflecting to the same point. And here I want to mention that if you try to locate interval between these two lines, so this is 2 pi I, this is 2 pi I. So this also represents that the function is periodic, and the period is 2 pi I. Now let's try to locate the final line that I'm intended to, and that is this line, this violet line I'm talking about. So it is little below the real axis. That makes this is pi by 2 minus pi by 2. This angle is minus pi by 2 I, minus pi by 2 times I. So it is making a small angle which is below, and this you can locate it here. Now we are going to talk about the vertical lines. So vertical lines we defined as L equal to x0 plus I times y0. So here the whole story is that x0 is fixed and y can be y, which is the argument part, that is varying. So x0 is fixed to the set of real numbers. We can choose different fixed values of x0 and then we can see the images. So e to the x0 plus I times y, this is equal to e to the x0. This is the radial part that defines the distance from origin for the polar form. And then we have e to the iy, where y is the polar part, which is kind of theta. So here y you can look as theta, and that theta you can roll from minus infinity to plus infinity via 0. So here e to the iy will be, or e to the I theta is cos theta plus I sin theta. So theta is going to be a periodic in terms of 2 pi, or you can say y to be periodic in terms of 2 pi, and that is going to repeat over and over. Let us try and handle this. Now let us suppose that we have some, we are considering this as a real, this is a real axis, and the vertical one is imaginary axis. And now we are going to consider a vertical line which is exactly the imaginary axis. So here we are considering this to be reflected in the W plane. Now here that x is equal to 0 for this line, x is equal to x we are calling x0, and this time we are setting the first value of x0 as unity, 0. So e to the 0 will be 1. So we are looking forward at some or to some point which is at unit distance from origin of the coordinate system. And y can roll from minus infinity to plus infinity. So here we are going to track a circle of radius 1. So here we are going to track a circle of radius 1. So when we will track this, when we will roll from 0 to 2 pi I, that is a period. So when we reach up to 2 pi I, so I am talking about this very portion of the line, and that traces a circle. So if I go beyond, it will trace the circle again, and downwards also similar thing is happening. Next we shall consider x is equal to some value which is higher than 0. So let us consider that this is some higher value. Let me pick another color. So I am talking about this line. Now when I am having a value higher than 1, so exponential will have a higher value. So I am talking about tracking a circle of radius greater than 1, and it is repeating over 2 pi I period. So this very portion of the line, this portion of the line I'm talking about, this will track a complete circle. So further higher values will track circle of radius, higher radius, and obviously here we are trying to show with the green dotted line higher value of x, and that will track a circle of higher radius. You can see. So here we are tracking a circle of higher radius. This one. When we are having smaller values of real, negative values of real part, so this is a negative value. So here you will be having x0 being replaced by some negative value, and this quantity will be less than 1, and you will be able to track this circle for that. This circle. this one, and then further for this value of x which is negative, we are having again a circle of smaller radius, and that will go on getting of smaller and smaller radius. Now to further understand mapping, we shall try to map the vertical strip from the z plane to w plane. Now here we are having a strip, and that vertical strip we are considering where y is having values from minus infinity to plus infinity, you can say, and here this strip is of unit width. You can call this as x equal to 0, and this is x equal to 1. Now e to the 0 will be 1 and e to the 1 will be 2.718. So the value of e I am writing as 2.718. So here this vertical strip we want to map, and the variations are from e to the 0 to e to the 1. So we have variation e to the 0 is 1 and e to the 1 is 2.718. So we are talking about the strip which is shaded here is corresponding to this. So this whole portion appears something like this. Now here I am talking about pi by 4. I am having value of y equal to I times pi by 4. This is my y. So this is pi by 4. So the angle pi by 4 is being represented here by this dotted line, and now the portion I'm talking about the line y equal to 0. So y equal to 0 will correspond to something like this. So here this is the different color shade for the strip which is corresponding to the mapped version of the exponential function to the set. Now the question is when e to the z is equal to 0, that we are trying to address. E to the power z is equal to 0, it means that e to the x into e to the y is equal to 0. So product of two numbers is equal to 0 where one of the numbers is 0. Here e to the y has absolute value 1. We have seen this. This can never be 0 because e to the iy, we are trying to write absolute value of this. This will be under root of cos square y plus sine square y. So this will be unity always. This will never be 0. So if you go diagram wise, we have seen that it has some value which is on this circle of radius 1. So this will never be 0. So the left option is that this should be 0. E to the x is equal to 0. E to the x will never be 0 for any value of x. We have seen this earlier also. So when we try to plot x here and e to the x here, then the function is like this. So for x is equal to 0, this has value 1 and it is never 0. Like exponential function is never 0, similarly the complex function is also never 0. It will be never 0. Now for given complex number z, which is belonging to the set of complex numbers except 0, there is w that belongs to the set of complex numbers such that e to the w is equal to z. So here we are trying to write the polar forms of both the functions. So here z we can write as mod of z e to the I theta, and w is equal to u plus iv. So this is equivalent to e to the w is equal to z. So that's what we are trying. So w we want to replace by u plus iv. So here we are replacing this w by u plus iv, and we are factoring the radial part and the angular part. And z we have written as mod of z into e to the I theta. Now we want to equate these two numbers. When two numbers which are in polar form, they are equal when their radial part is equal and argument part is also equal. So for that equality, we are trying to write e to the u is equal to mod of z. So this is for the radial equivalence, and for angular equivalence, argument equivalence, we have e to the iv is equal to e to the I theta. So obviously this v you can write as theta plus 2 pi k. So here we are taking care of all the possible cases. And then for this to be equal, you have u to be equal to log of natural log of mod of z, and v is equal to theta plus 2 pi k. And then we have w is equal to expressed in the form as logarithm of natural log of mod of z plus I times argument of z. So this is complex logarithm. Now we want to extend our ideas that we have developed for exponential function to the complex trigonometric functions. So e to the I theta, we have done partially that. E to the I theta is equal to cos theta plus I times sin theta. And then e to the minus I theta, here we are going to replace theta by minus theta. So cos of minus theta plus I times sine of minus theta. This is a symmetric function, and cos of minus theta is equal to cos theta, and this is anti-symmetric function. So sine of minus theta is equal to minus sine theta. So here we have e to the power minus I theta expressed like this. Now when we add e to the I theta plus e to the minus I theta, we are adding cos of theta and cos of theta. So that makes 2 times cos of theta. So this term is cancelled out. And when we are subtracting e to the I theta from e to the minus I theta, so what we are doing, we are cancelling cos and we are adding sine theta times I, so that returns a value 2 times I sine theta. And now we can raise this to write cos of theta and sine of theta. We have to just divide the equation by 2 in the first case and 2i in the second case. So we are in position to define cos of complex function z as e to the iz plus e to the minus iz upon 2, and sine of z as e to the iz minus e to the minus iz upon 2i. Now we have these two definitions at our disposal, and we are going to understand more about the properties of sine and cosine complex functions. So sine and cosine are analytic functions that we already know. And for real values of z, it means that real part is x, imaginary part which is y, we are setting to 0, then the complex sine and cosine agree with the real value of sine and cosine functions. That is for sure. Now e to the cos of minus z we are trying to raise. So to raise cos of minus z, we have to replace z by minus z at every place. So here z is replaced by minus z. So there is just flip of terms. E to the minus iz plus e to the iz. So addition is commutative, so that is cos of z. So this function is a symmetric function, again like in real valued cosine function. Similarly, sine of minus z, so here by definition we shall replace z by minus z at every place, and we shall rewrite that, and here you will be able to realize that it is minus sine of z, so it behaves in the similar way as it behaves in real domain. So cos of z plus w, we are extending the formulas. Cos of alpha plus beta, we write cos alpha cos beta minus sin alpha sin beta. So here we can extend our definitions of addition of sine and cosine function. So cos of z plus w, where z and w are two complex numbers, we have cos of z cos of w minus sine of z sine of w. Similarly, sine of z plus w is equal to sine of z cos of w plus cos of z sine of w. Now we shall prove what we have written earlier. Cos of z plus w is equal to cos of z cos of w minus sine of z sine of w. Let us plug in the values of the functions for right hand side term, and cos of z will be e to the iz plus e to the minus iz upon 2. Cos of w is e to the iw plus e to the minus iw upon 2, minus so on, similar things I am putting. And here 2 into 2, 4, and that is 2i into 2i, it will be 4i square, that is minus 4, and minus 4 into minus, so we have denominator common, that is 4, and we have to expand this bracket. A plus b into c plus d, we can expand it like, and here you can see on the screen that we have the terms written for all quantities. E to the iz into e to the iw, this quantity plus e to the iz into e to the iw, that makes it 2 times. Then e to the minus I z into e to the minus iw plus e to the minus iz into e to the minus iw, that makes it 2 times. And the other terms, e to the iz into e to the minus iw, will cancel with this. Then this term will cancel with this. And here we can cancel 2 with one of the 2 in the denominator, and we can write e to the I times z plus w plus e to the minus I times z plus w, that is by definition cos of z plus w. Now cos of z we have definition, and sine of z we have definition. So cos of z plus 2 pi, if we try to write, we have to replace z by z plus 2 pi at every possible place that is available, and this is equal to cos of z because it has cosine function has period 2 pi. Similarly, sine of z plus 2 pi is equal to sine of z, and then we can again prove sine square z plus cos square z is equal to 1. Similarly, sine of z plus pi by 2 is equal to cos of z. So sine of z plus pi by 2 is equal to e to the power z plus pi by 2 minus e to the power minus I times z plus pi by 2 divided by twice I. This is by definition. Now we can rearrange things. I times e to the iz we can write for this quantity, and for this quantity we can write minus I times e to the minus iz, and this we can further simplify as cos of z. We are looking for when sine of z is equal to 0. By definition, sine of z is equal to e to the z, e to the iz minus e to the minus iz upon 2i. So sine of z will be 0 when numerator will be 0, and when numerator will be 0, you have e to the iz is equal to e to the minus iz. So e to the iz, we have iz minus of iz, this is equal to 2 pi ki. So this is the possible condition, and this offers us that z is equal to k times pi, that is integral multiple of pi. Similarly, we can extend it for cos of z is equal to 0 when z is equal to pi by 2 plus k pi. Now we are in position to differentiate this sine and cosine functions, and d dz of sine of z, we have to replace sine of z by our definition e to the iz minus e to the minus iz upon 2i, and then we are differentiating this bracket with respect to z. Now we have learned derivative of exponential function. E to the iz will have derivative I times same function, and derivative of e to the minus iz will be minus I times e to the iz. So placing it respectively, and here this minus minus will be plus, and you can cancel this I, and this I. So e to the iz plus e to the minus iz upon 2, this is cos of z. Similarly, d dz of cos of z is minus sine of z. I would advise students to pick up a piece of paper and explore these formulas to have a better realization of what we are doing. Now we are trying to relate the quantities to hyperbolic function, and sine of z we are writing as sine of x plus iy. Now we can extend the formula. Sine alpha plus beta is equal to sine alpha cos beta plus cos alpha sin beta. So here alpha is x and iy is beta. So here further we can write cos of iy as, see, this iy is the angle, this is the argument. So e to the I times iy plus e to the minus I times iy upon 2 will make cos of iy. Similarly, sine of iy will be e to the I times iy minus e to the minus I times iy upon 2i. So here we can extend I square as minus 1 and e to the minus y plus e to the y upon 2, and here e to the minus y minus e to the y upon 2i. So here we can simplify this as a convenient way of expression, and here also a convenient way of expression. So this is cos of y and this is sinh of y. So sine of z we have expressed as real and hyperbolic trigonometric functions as sine of x cos of y plus I times cos of x sinh of y. Similarly, we can express cos of z as cos of x cos of y minus I times sine of x sinh of y.